In part 5 of load switch design, we'll focus on inductive loads, once again ensuring that the path switch stays safe. Here's a list of load types again. Inductive loads like relays and motors store energy using magnetic fields while current is flowing. When the load switch turns off and current flow is interrupted, the collapsing magnetic field induces a voltage that opposes the change in current, and this is commonly referred to as back-EMF. The level of induced voltage follows the inductor equation, so it's proportional to the inductance of the load and the rate of change of current. Because load switches turn off quickly, the current changes from its steady state value to zero over a very short time, causing an induced voltage to spike until it's clamped or a device fails. In the MOSFET, exceeding the maximum VDS forces it into avalanche breakdown, clamping the voltage but stressing the device. This is shown in the waveform here. The voltage is clamped at negative 30 volts, which is the VDS limit of the path switch. In spacecraft, for example, this is generally avoided because avalanche operation increases susceptibility to radiation-induced damage. You can also see that quite a bit of noise is generated from parasitic LC resonance as the switch exits avalanche. The way to get around this issue is to add a catch diode. A catch diode, which can also be called a flyback or a freewheel diode, improves turn-off behavior for inductive loads. For a high-side load switch, when current flow from the source is interrupted, the inductive current drives the output voltage below ground, and the catch diode clamps it at roughly a diode drop. This provides a controlled current path for stored energy to discharge. In the waveform comparison, you can see that the current decay is spread out over a longer time period, reducing DI/dt. The output voltage plot also shows the lower clamp level and the reduction in parasitic ringing. Effectively, what we're doing is limiting VL to a diode drop. Since L and delta I are consistent, the clamping diode increases delta T. Good diode options for back-EMF suppression include the ES1D and similar series. There's plenty of other good options, including a similar line of diodes like the MERS 120. But for the ES1D, the naming convention is broken down here. The first one or two characters refers to the recovery time of the diode. The next digit is the current rating, and the last letter is the voltage rating. Recovery time isn't a critical parameter for this application, because the current through the diode decays continuously instead of being abruptly forced to zero. ES1D is chosen mainly because there's a default model in the LT-SPICE part library, and because Nexperia has a pretty great datasheet for this part. These kinds of diodes are commonly found in the SMA, SMB, or SMC packages, depending on the current level of the part. Other package choices include the SOD 128, 123, or 323, as long as you can make sure the package can handle the energy stored in the inductive load. ES1D is most commonly available in the SMA package, so we'll stick with that. Let's take a look at the key datasheet values for a diode. The upper left shows the diode in the reverse biased or off state. The first key datasheet characteristic for this state is reverse voltage, which is 200 volts for this part. From our requirements, we're only going to have 5 volts across it, so we're definitely good there. The other key characteristic for the off state is reverse current, which is the leakage current. This one has 5 microamps at room temp, which is still pretty low compared to the 1 amp load. Because only a small percentage of the rated reverse voltage is used, the leakage should be a bit lower. When the diode is forward biased, the max room temp forward voltage is 950 millivolts, and the rated average forward current is 1 amp. The peak surge current is much higher, it's 30 amps. Diodes also have suggested derating factors in various derating standards. Different types of diodes, like Zener's or TVS, may have different derating factors. In this case, we're only looking at general-purpose diodes. The derated values are shown, but junction temp limit is still the key parameter, and we need to make sure that the junction temp stays below 110 degrees C. So, in order to analyze whether the catch diode remains within this junction temperature limit, we can again use energy. To start, the equivalent circuit at turn-off is shown. We can find the equation for the current loop by using KVL and the inductor equation. Rearranging it puts it into the standard form for differential equations, which can then be solved with your favorite diff-EQ technique. Using the integrating factor is one approach, breaking it into homogeneous and particular solutions is another, and moving to the frequency domain, solving algebraically, and moving back to the time domain is a third. Regardless of which method you choose, the solution is shown here. Next, we know that at time 0, when the load switch begins to turn off, the current is at steady state, which is 1 amp for this example. You can use this as the initial condition and solve for C. This will give you the full solution for the inductor current. We know that after a certain period of time, the inductor current will reach 0 amps, so you can use this as the final condition. And you can do this by setting the left side of the inductor current to 0, and then solving for time to find T off. That solution is shown as well. Plugging in our part values into the equations found will give 4 milliseconds for the turn-off time. Now that we know the turn-off time, the thermal transient impedance graph from the datasheet can be used to find the appropriate thermal impedance for 4 milliseconds. Power can then be calculated using the allowed temperature rise based on the requirements and this transient thermal impedance. Last, energy is found using this power value and the 4 millisecond time period. A math solver program like MathCAD can be really helpful for these kinds of calculations. The nice thing about these programs is they keep track of units for you as well. There's a free version of MathCAD that has limited functionality, and then there's also a free for personal use program called SMath Studio that's similar to MathCAD. Using a math solver makes it pretty easy to compute the energy of the diode. Power of the diode is voltage multiplied by current, and to keep it a bit simpler, it's assumed that the forward voltage of the diode is constant. This is a conservative assumption since current is decreasing. Then, energy is the integral of power over time. The time period is the T-off value we found earlier. The solution to the integral is also shown, and it's not a particularly difficult integral to solve by hand if that's your preference. After all this, the energy of the diode ends up being much smaller than the energy limit for the part, just about 1/25th, so it's definitely safe for this level of current and inductance. This tells us that the supported inductance of the load can be quite a bit higher than 10 millihenries shown with this design, or you can go to a smaller package than SMA if the design was space constrained. So here's the final look at the load switch design that can safely handle both inductive and capacitive loads. The waveforms for drain voltage and FET current are shown. The waveforms show that the voltage is slow to rise for the inductive load, since we're limiting the ramp rate using the C-limit charging approach. There are situations where the inductive load requires a fast dV/dt transition to turn on, and keeping the capacitive load protection in place doesn't work well with that. So the solution for this can be to keep the same basic switch design for all loads, but then to selectively leave parts uninstalled. In this case, the turn-off speed-up BJT and the C-limit capacitor are marked as do not install on the parts list or BOM. For R-limit, it should be replaced with a 0 ohm resistor. The updated waveforms for this configuration are shown. The dV/dt transition for Vout is now much faster, and the switch is still protected during turn-off.